formally start the course on linear algebra and stochastic process, right? So we have three parts in this course. One is about its probability, and then we have random process, and then linear algebra. So I go in that order, right? So as you have already some fundamental knowledge, right, about this probability, right, random process and all is there. You already studied in UG, right? So we straight away start with the change of random variable, right? So today we are going to discuss about that. Transformation of random variables. So this is needed, right? For example, if I want to generate the Gaussian data, right, in a program, right? So what we do, we start with generating that uniform distributed data, RAND. There is a command called RAND, right? It generates the uniform distributed data, right? The outcome of the random variable is of uniform distributed. So we have like 0 to 1 fx of x. This is the uniform distributed, right? So then we convert them into the required distribution. Either it is going to be the Rayleigh distribution or Gaussian distribution, whatever it is, right? We have the methodology to convert from one random variable to that another random variable. The transformation of random variable will always exist. For example, we discussed about y equal to x plus n problem. It is again a transformation of random variable, right? We had a random variable called x, and we had the random variable n, which is associated with that noise, and we got the random variable y, right? So we have the transformation of random variable possible, right? So let us take more general. We have like this two random variables, right? So we have this x1 and x2, they are the random variable. They are related to that another two random variable y1 and y2 using that function g1 and g2. g1 of x1 comma x2 is y1, g2 of x1 comma x2 is y2. And the function what we have chosen is invertible one. It means that I must be able to identify what is my x1, right, using another function, right, h1 of y1 comma y2, and then x2 as h2 of y1 comma y2. The question is, if you are given the density function of x1 x2 joint density function combined together, right, will it be possible to get the density function of this? And remember that this y1 and y2 as a function of what? x1 and x2, right? So let me make it as more general in this. If it is alpha and beta, it should be again the function of what? Alpha and beta, right? So we have a relationship between what? These two joint density function. So anybody knows this result? Have you heard about this Jacobian method of transformation of random variable, right? That's what exactly we are going to discuss today, right? So let us consider right? So this is a set of all points x1 and x2 which forms a, right, a small piece of rectangle here. So I am looking for, right, after transforming into this, that function, right, you get the related graph with reference to what? y1 and y2. What I am trying to say here is, I have a line in which I am following this one as a set of all points where this x1, capital X1 is lowercase x1, right? It's constant. And I have here x1 plus delta x1. So this is the line. So I have set of points on that. So this is the line what is considered, right? And of course here this x1 is fixed and we have set of all values for what? x2. Strictly speaking, starts from where? Minus infinity to plus infinity. Similarly for here it is like that. You are fixing it up capital X1 and x2 is ranging from minus infinity to plus infinity. It is like that. Similarly, I can think of here x2 and this is what? x2 plus delta x2. And I am finding the region of overlapping. Right? So you know what is that coordinate here, right? So these 4 coordinates is known to us. Right? Right? So now these lines, after applying the function, for example, I have to apply the function g1 and g2 because it is a function on what? x1 and x2. Right? So if I apply that function for these points, I get some curve. Right? So let me draw that curve here. See, because I am fixing, for example, this line, if I consider, I am fixing it at what? x1 and your x2 is changing, right? So this one I am fixing and you are getting that function of what? x2, right? It is going to be what? y1. And similarly when I use this g2, again what? x1 is fixed and it is going to be the function of x2. And you get that points, right? y1 and y2. So I am just collecting those points, y1, y2, and that one I am plotting in this graph. Right? So if I do that, I get some arbitrary curve. It may not be like this. Exactly like this. You get some arbitrary curve here. This is clear to you, right? So what is this curve indicate? This curve indicates that set of all points y1, y2, right? Which is given like this, when x1 is equal to what? x1 here, and this x1 is equal to x1 here, right? And it is going to be the function of x2, right? To be more precise, what I am trying to say here is g1 of what? x2, g2 of x2. I am writing it as the function of x2 because I have fixed the value of what? x1. To be more precise, I can write that also by fixing the value of x1, capital X1, and I am finding out all the points y1 and y2, and that is going to be this curve. Right? Similarly, I can think of another strip like this, right? And we have this another strip, right? I don't have further colors, right? So I use again white, like this, right? So this curve is by fixing x1 equal to smaller case x1, right? And this curve, what I get here, this is again this g1 of x2, g2 of x2, but you are fixing it at what? I am writing that x1 alone, delta x1, and it is going to be the same. It is a function of x2 both. In one case I am fixing it at what? Capital X1 as small x1. The other case I am writing it as what? Capital X1 as x1 plus delta x1. Right? And similarly, okay, we can go for this two curve here. So now this case I am talking about this line. In this case I am fixing it at what? x2, and it is going to be the function of x1, right? So let me write it here. This is going to be what? g1 of x1, g2 of x1, keeping what? x2 as x2 here, right? This one I'm talking about. And you have this curve here. This is g1 of x1, the same thing only, right? So g2 of x1, and you are keeping what? x2 as x2 plus delta x, right? And you have this area of intersection of these four curves. The idea is basically, is it coming through the speaker right now?
Yes.
Right? The idea is the probability associated with this region. This region is what? This is delta x1 here, and this is delta x2. The area is delta x1 times delta x2. If I want to find out the probability, if you are given a density function, what you do? You find out the density function at x1 comma x2 and then multiply with that area. If for 2D, if it is 1D, what you do? You take area under the curve, right? For 2D, what you do? You have to find out the location. For example, at this point x1 comma x2, I would like to know what is my probability. Probability is not defined at a point because the density function is not going to give you the probability. We need at least the minimal area which gives you what? The probability around that point. So if I keep that point x1 comma x2, and if I want to know what is the probability around that region, the region what I have considered is what? x1 plus delta x1, and then what? x2 plus, this side it is delta x2, this side it is delta x1. So the area is what? Delta x1, delta x2. So if I multiply delta x1 times delta x2 times the density function at what? x1 comma x2, right? I write that one here. This is delta x1, delta x2. This is equal to the area what you have here. This area, we don't know that, so we can approximate that it is the area of, right, the parallelogram, right, into what? Into the point what we are considering, right? So, for example, this is the reference point, right? So x1 here. So this point is going to be your y1 comma y2, right? Right? So you are finding out this density function. We don't know the area, but I am writing this y1, y2, right, as what? y1, y2 here. But remember that this y1 and y2 is going to be the function of what? x1, x2, right? So I write it as like this: x1 comma x2, x1 comma x2. Or in general, this is going to be what? F, this is equal to, I write it here, area of the parallelogram what we are considering into what? F y1, y2 of, simply I call it as x1 and x2. Nothing wrong with it, because finally it is going to be the function of x1 and x2, because I want to equate x1 and x2 here, right? So this is what I want. So the problem is very simple, right? So what we had it here, this x1 and x2 are arbitrary value. I can put even what? Alpha comma beta, that doesn't matter. It is some arbitrary point what we have chosen. So like this, alpha beta here, alpha beta here. We need a relationship. The relationship is readily available. What is left out or what is not known is this area of what? The parallelogram. So once it is known, then you get a result, right? So we will consider this as a parallelogram here, this box, right? So if this is a reference here, and if I know these coordinates, I can find out this vector, isn't it? How? See, this is that, no? So I get this vector and this vector. I get this too, right? This is the vector A, and this is the vector B. Then what is my area of parallelogram? It is just the cross product, A cross B. If I know the coordinate, I can go for what? The determinant. directly I can go for what? Determinant to know about this area. So what we need is this coordinate and this coordinate. That's all. Right? How will you find out that? So this is the point here, y1 and y2, right? So how this first value is getting changed? How the y1 is getting changed? But remember that as far as this curve is considered, you have already fixed. What is that? It is fixed, right? x2 has what? x2 plus delta x2. And of course we have this curve here, this curve. In this, what is fixed here? x1 as? Okay, we will have a small changeover for simplicity. Let me take this one as x2 here and this one as x2 plus delta x2. Okay, I mean this curve is x2 equal to x2 plus delta x2 and this one is x2 equal to x2. And this one is x1 and this is x1 plus delta x1. Small change over here, right? So now let us consider this curve where we have fixed what? x2 equal to x2, lowercase x2, right? So we would like to know how this x2 is changing. I'm sorry, this y1, this coordinates, y1 is changing by changing the value of what? x2, because this curve we already fixed what? x2, so it is going to get changed only with what? x1. Isn't it? So by changing x1, both the values y1 as well as y2 both are going to get changed, right? So we would like to know how this y1 is getting affected with what? This x1. Isn't it? Because x2 you already fixed. You already fixed what? x2, right? So you would like to know what is that? How this value, you already fixed what? Let us say this x2 is fixed. So this g1 of x1, right? The rate at which this g1 of x1 is changing by changing what? x1, right? So what does that mean? Dou g1 by dou x1. It is the rate at which this g1 is changing with respect to what? x1, right? But the actual difference here is happening what? Delta x1. The rate at which it is changing is dou g1 by dou x1. The changeover actual happened is what? Delta x1. So what is the change actually happening? Dou g1 by dou x1 multiplied with what? Delta x1. Got it? Right? But that is only the changeover. The original value is what? y1. So that coordinate is going to be what? y1 plus, so let me call this as a coordinate p and this as q here. So what is that you say about this p? Dou g1 by dou x1, right? Because you already fixed x2, isn't it? And that is getting multiplied with what? Delta x1 plus what? y1. This is the first coordinate, I mean among that. The next one is what? This y2, right? So you have the expression dou g2, right, is changing with what again? The same x1, because x2 is already fixed. So this is dou x1, right? And it is getting multiplied with what? x1, isn't it? Delta x1 plus what? You are getting plus what? y2. Right? Can you tell me now what is that coordinate for q? The coordinate for q is this curve. This curve you are fixing up what? x1. So you are again going to use the same g1 and g2, but this time you are going to differentiate with respect to x2 instead of x1. Again, the difference happening here is corresponding to what? Delta x2. Here it is going to be delta x1 in both the case, and there it is going to be delta x2 in both the case, right? So the point Q, if I want to know, right? So again, it is going to be dou G1 by dou X2 into what? Delta X2 plus Y1. The same point what we are considering here, right? And then you have this dou G2 by dou X2 delta X2 plus. So can somebody tell me what is the area of the parallelogram in this? So we need to know about this vector A and B. What is the vector A? We have the both the coordinate. Now only it is coming. Okay, right? So now tell me what is that vector A? Vector A is the difference in the coordinate. Got it? So here this coordinate is y1 plus something, right? So the difference is, except this y1, whatever is there, that is going to be that difference, A vector. So if I want to know about this A vector, it is simply what? I can write it here. So this area of parallelogram is my determinant here, right? In which we need this A vector to be written and then what? B vector to be written, isn't it? That is going to be your A cross B, isn't it? So the difference in that coordinate is what? Dou G1, dou X1 into what? Delta X1, right? That I will write here. And this is going to be dou G2 by dou X1 delta X1 here. And then here it is dou G1 by dou X2 into delta X2 dou G2 by dou X2 into delta X2, right? And I can take this delta X1 and delta X2 outside, right? So I do that now. Delta X1 delta X2, and these two gets cancelled, and this matrix is what we call it as Jacobian matrix. This is called Jacobian matrix J. In fact, determinant of this Jacobian matrix. So that is the way how it is getting related, right? You told that it is known to you, right? Is it fine? Right? So what is the relationship now? Finally, the relationship I will write it here. F y1 y2 of alpha comma beta, that is equal to what? 1 by Jacobian. So I am bringing the Jacobian to the right hand side. F x1 x2 of x1 comma. I'm sorry, this is alpha comma beta. The same. Right? Jacobian, you know what it is. Jacobian means this, but computed at the point. We need to compute at the point where you are trying to find out what? This probability, right? What is that? It is going to be your, this, in this case we are talking about this x1 comma x2. Right? So the relationship is like this. Jacobian, you use the function what? G1 and G2, these two functions, right? We will do some examples so that it will be more clear. Let us have the transformation of random variable like this, right? So you can even write this one in this form. Right, you have this R and theta. This is most important in communication engineering, which actually leads to the Gaussian distributed. We'll see how it is going to happen. Right? So let us have this one as what? R equal to root of x squared plus y squared. And theta is tan inverse of y by x. Right? And we can write this one in this form also. I mean, we take this just a confirmation for that function is what? Invertible, right? So x is r cos theta, y equal to r sin theta. In fact, we can straight away write this fxy of x comma y is what? 1 by Jacobian of this what? Fr theta of r comma theta. This is actually should be what? The function of what? X and y individually. We have to find out this, right? We already know it is going to be the function of what? R is a function of x and y, and theta is also the function of x and y. And finally we write this expression in the function of what? X, y and y, because we need the density function as a function of what? X and y. So this is the way how we do, right? So now we quickly find out what is a Jacobian. Jacobian is basically the determinant that we use this function here because I need the density function here like this. So I use this as a function. So this is like, you know, g1 of r comma theta here, and this is what? g2 of r, let me put it as capital, r comma theta here, right? So what we write here? Dou g1 by dou r, dou g2 by dou r here, and dou g1 by dou theta, dou g2 by. So this is what? Differentiating with respect to r, it is cos theta here. Differentiating g2 with respect to r is sin theta here. With reference to theta, it is minus r sin theta, and g2 with reference to theta, it is r cos theta. So this is going to be magnitude r here. So I write it here like this, 1 by r, right? So but we know what is r, right? The magnitude of r is what? Root of x squared plus y squared, but take the positive value. So that's what we need to put here, right? So I'm writing that. So fr theta of what? R comma theta. In fact, if I put small r here, I have put here small r, right? So but you know what is that r? R and theta. Lowercase r is what? Root of x square plus y square, and theta is tan inverse of y by x. This is the way how we convert, right? In fact, the other way around is also true. For example, what I am telling here is fr theta of r comma theta is mod r fxy of x comma y, where x and y we can write in terms of what? R and theta. The other way around is also true. But here I need this result to be in the function of what? R and theta. Right? Let us consider this density function is Gaussian. fxy is Gaussian. If we see what will happen to this distribution, right? We'll see that. So fxy, we substitute that fxy of x comma y as 1 by root of 2 pi sigma square e power x squared by 2 sigma square, and then we have one more time 1 by root of 2 pi sigma square, so I take square there, and this is going to be minus y squared by 2 sigma square. We have assumed that the mean is 0. The mean of x and y is, are 0 here. Variance sigma square. Both are Gaussian distributed, right? And of course they are uncorrelated and independent, because I am writing the product of what? The marginal density function. If it is not, then we have to go for multivariate Gaussian density function. We are going to discuss in the coming classes. Multivariate Gaussian density function, where the covariance matrix is not the diagonal matrix. But this case, the covariance matrix is the diagonal matrix. Covariance matrix, the diagonal elements or the variances, simply sigma squared here and here sigma squared. That's it. And these values are 0. Of diagonal elements are 0. It is going to have only what? the diagonal elements with what? Sigma square, and these two values are what? 0. And that's what we are able to write as what? The product of the marginal density function. Now what I am asking is, I want this fr theta of r comma theta. This is what? We need to write this magnitude over here by, and this is becoming 2 pi sigma square here, and this is, I want to write this one in terms of what? R and theta, but we already know x squared plus y squared is what? Is r square, isn't it? So we get e power minus r squared by 2 sigma square, and most important is this r is greater than or equal to 0, because we already know that. What is that? Right? It is positive quantity. Right? And of course this theta, you may wonder, it is not explicitly available. Right? Right? So, but it is the function of theta also. It is happening because it is a constant. The density function for theta, it is constant. When it is constant, you will not get theta. So what it means really, it is of uniform distributed. Theta is uniformly distributed between what? 0 to 2 pi. And that is what? Theta is not there in this sphere. And you get like this. This is 0, this is 2 pi here, and this is 1 by 2 pi. Right? Isn't it? So, if we remove this 1 by 2 pi in this, I get a distribution r by sigma square e power minus r square by 2 sigma square, where r is what? Greater than or equal to 0, and that distribution is called Rayleigh distribution. This is used in telecommunication. The channel model, what we use is, is the Rayleigh channel. We used to say like that, the Rayleigh channel. We are saying that it is a Rayleigh channel because, right, see these things, this X, Y, R are coming because of baseband transmission. In phase and quadrature component, they are actually, in case of baseband transmission, whatever you transmit through the channel, they are complex signals. Don't get confused, right? There is nothing like a complex signal being transmitted through the channel. It is properly converted into the what? The real signal, which we call as baseband to band pass conversion using this carrier frequency. You have in phase and quadrature component. On paper, you write it as what? Xi plus j into x cube. You have this what? In phase and quadrature component, which is being transmitted through the channel, which is a complex in nature. It doesn't mean that you are transmitting complex number, no. It is only on the paper, which we call it as baseband transmission. Right? And we convert this quantity, whatever I told, this complex number, into what? The real quantity is what we call it as baseband to band pass transmission. For doing that, we need to include the carrier frequency. Xi cos 2 pi fct minus x cube sin 2 pi fct will become the band pass transmission xt. We are going to discuss in detail in the coming classes. That's what I am not writing on the board, but we are going to discuss that. Right? But what I want to say here is, right, in that case, the noise what we consider in the baseband transmission is also complex. The noise what we consider in baseband transmission equivalent, it is only on the paper, don't get confused, right? It is not that complex number you are transmitting. On the paper, we analyze only the baseband, because it is after all the conversion from this to band pass just by using the carrier frequency. We can use any carrier frequency for what? The translation. So the analysis part in telecommunication, they do only with what? The baseband transmission. As far as its baseband transmission is considered, right, the noise component is no more real, it is complex. Because the noise gets added with what? The in-phase component as well as what? The quadrature component. So that is becoming what? The complex. Right? So in that case, the magnitude of the noise, if we consider, that is exactly like this. This is the in-phase component of the noise. This is quadrature component of the noise, and this is going to be your magnitude of the noise. And if in-phase noise, quadrature noise, they are Gaussian distributed, that is nature, right? We are considering even the previous example, x plus n, we consider the noise is what? Gaussian. Here also I can assume this x and y, the noise associated with what? The in-phase component and quadrature component both are what? Gaussian. If that is the case, what is the distribution of R? It is Rayleigh distribution. And that is why we call that channel as Rayleigh model. Rayleigh model channel, right? Rayleigh channel. This is very important, that's what I'm telling you. So that the magnitude of the noise is actually now, this way it is distributed, R by 2, sigma square e power minus R square by 2 sigma square. Here it is just sigma square, not where R is what? Greater than or equal to 0. And this 1 by 2 pi I just removed. It means that your R and theta here, they are independent. This is written as f theta of theta and f r of r. F theta of theta is what I have marked in yellow, right? 1 by 2 pi. What does it mean? It means that theta is uniformly distributed between what? 0 to 2 pi. It is done now here. And we have this another component in this. This is the Rayleigh distributed. R by sigma square e power minus R square by 2 sigma square. They are what? Rayleigh distributed. But remember that as we have a close relationship between what? The Rayleigh distribution and what? The Gaussian distribution. Because from the Gaussian we are getting this. That is a way which gives you what? Gaussian from Rayleigh also, isn't it? That intuitively we are able to understand, but we are going to discuss the formal way of what? Getting the Gaussian distributed data from where? The Rayleigh distributed data. All are what we call as transformation of random variable. It's very simple. From this expression we are able to understand that if R is Rayleigh distributed and theta is uniformly distributed between 0 to 2 pi, then x equal to R cos theta is what? Gaussian distributed. And we have two choices for it. Y equal to what? R sin theta. That is also going to be what? Gaussian distributed. So if I have a Rayleigh distributed data, if you are having Rayleigh distributed data, then I can generate what? Gaussian distributed data straight away. But how to get Rayleigh distributed data is a question mark, right? So I told at the beginning, right, we can do it from uniformly distributed data. I tell you how that is done. So the steps are like this, So for getting this Gaussian data, so in the MATLAB, you have a command called rand_n. That is what? Normal distributed data. Rand is what? Uniformly distributed data. In fact, the rand is known to you, right? So that is using this PN sequence they generate using some seed, initial seed. That is only random. That is only random what they are generating. All other distributions are coming from that point. They generate always uniform distributed data. That is the starting point. All other density function, whatever you want, either it is Rayleigh or Gaussian, chi-square, whatever it is, all the other distributions are coming from that. With what we call it as transformation of randomly. We do the transformation and we get it. Right? So for example, in this case I told, if I have Rayleigh and uniform distributed data, but this case uniform distributed, that value should be what? 0 to 2 pi, not 0 to 1. If that is the case, what will happen? R cos theta will give you directly what? Gaussian. R sin theta will also give you what? Gaussian. Exactly this is what they use it in random. But I didn't say how this R is generated. Right? You need this R also to get generated. Then R cos theta will give you X. isn't it? So we'll have a motivation of how we will stop here, right? So next class tomorrow you come on time, right? So we have you have 10:30, right? Tomorrow, so you can come by 10:30. Who is maintaining the attendance? Someone can maintain. Yes, right? Okay, we'll stop here. Any doubts in this? Tomorrow we'll have come directly here. I will come directly here, right? 10:30 we'll have it. Next questions. We'll stop here. Okay.
What about temporary card? Will you get it after lunch or what? Temporary card. Temporary ID, but that's no problem.